Hello, my name is Sean Perry, and welcome to a lecture series on Calculus 3, or multivariate calculus. To begin with, we're going to look at an overview of Calculus 3. To begin with, the central concept of Calculus 3 is that we are going to extend notions from Calculus 1 and 2 to include perhaps several variables of input or output. That is to say, we will consider functions who both take in several real numbers as an input and give you perhaps several real numbers as an output. But which concepts are those going to be? Well, let's begin with the concept of a number. This is a single quantity that we assign some real number to. And what we might consider then are several of these quantities. Now, there's a little bit more to vectors than that, but the main idea is that a vector, instead of being a single number, will be an ordered sequence of numbers. We're going to be interested in particular in 2 and 3, but one could imagine actually having any number of these, any finite number. And this would still be in some sense a vector, and in that regard, sort of the main player of the story of Calculus 3. But then we're also going to consider derivatives and integrals, how those will change. Well, perhaps this deserves a new board. So let's list our Calculus 1 and 2 concepts over here. And let's list our Calculus 3 concepts over here. And sort of explore a little bit about how these are going to change. We talked just a moment ago about numbers. And we might think of these as some position on the number line, where all of our usual numbers live. Maybe that's a 1. No, that's nearly 3. So maybe that's a 1. On the other hand, what about vectors? So a vector is sometimes described as an ordered pair of these numbers or it's sometimes described as a thing possessing both magnitude, like a number does, but also direction. But we can also think of these as sort of positions or arrows pointing to positions in space. So in the case of R2, this is the plane of numbers, as opposed to R1, the line of numbers. You're used to giving some kind of x and y coordinate and treating this as the coordinate pair x, y, a single object which represents two quantities. And the only difference, which is going to seem pretty subtle for right now, is that we are going to instead consider this to imply a direction. That is to say, going from the origin to this point. We could have done this in R1, of course, right? We could consider these as directions pointing from the origin to the number. And in that regard, numbers are also vectors. A number is a one-dimensional vector. Vectors are going to have their own kind of algebra associated with them, their own kind of possible operations that you could do to them. And those are going to be larger and more general than what we can do with numbers. Notice that there is no really intuitive way that we could just talk about multiplication of some two vectors, but we obviously know what we mean by multiplication of an integer or a real number. So something more peculiar is going on with these guys. But we'll talk about these in much more detail in a later video. For right now, the next thing that we would want to extend are functions. So we talked about functions of a real number. So let's say functions which take in a real number and give you a real number back, right? That's what we learn about in Algebra 1 class. No big deal. We can visualize this with graphs. And generally, we would prescribe some rule for that, right? Like f of x is maybe equal to x squared plus x plus 1, something like that, right? Where a number goes in and some thing gets done to it, and that thing in the end is another real number itself. And we might also, if you did Calc 2 with me anyway, you looked at parametric equations. Parametric equations are a map from R, which will represent time, into some bigger space. Right, and in this case, we would give multiple functions, maybe an x function. Let's say we have, f of t is actually given by a couple coordinates, maybe like t and t squared plus 1. Right, and then you could get an ordinate point in some, let's say R2 here, by plugging in something, plugging in a real number, and having it several sets of rules that work out your output, each coordinate of your output. So these were parametric equations. So called because we can get all of the rules involved in terms of the parameter t. On the other hand, for Calc 3, we're going to be interested in different kinds of functions. We're going to be interested in, first of all, functions which take a vector in and yield some kind of real number out. You could think of this as being the height above some surface or above some region, giving you a surface instead of a graph. And quite simply, right, if we were to think of this as a function of more than one variable, we could come up with rules which, when we evaluate them by plugging in numbers, just give us a single number. Such a graph of this thing would look like a surface above a plane of x's and y's. On the other hand, a final step of generalization will occur when not only do we take vectors as inputs, but we get them as outputs as well. And in this case, you might have something, which takes in a couple of variables, and then each position, let me give it this as a vector this time, each position is given by working those out somehow. So sort of a natural combination of these two ideas. We have multiple places of output. We have multiple quantities of input. This is the substance of Calc 3. To continue with the metaphor, in Calc 1 and 2, we learn about the derivative. In Calculus 3, we're not just going to have a single input variable that we need to consider the change with regards to. We're going to have several input variables. So while this is the so-called derivative, Calc 3, we become interested in the partial derivative. And these will be written with a squiggly d. Squiggly d. Instead of a regular d. And we'll be interested in the case where there's a finite number of variables here, usually 2 or 3. And essentially all you need to know about what these are going to be, just to get started, is that we consider the derivative freezing the other variables and then choosing one of them to truly be a variable. So for example, let's say I was taking the derivative with respect to y of some expression xy squared plus y x squared plus 1. All I do is pretend x is a constant, because I'm not taking the derivative with respect to x, I'm taking it with respect to y. So x gets frozen, and we just pretend like it comes along as a constant for the ride, and the constant 1, of course, goes to 0. What about, there's also other notions of change, not just this kind of one variable gets allowed to move and the others are frozen kind of a sense. We're going to be learning about things like the gradient, things like curl and divergence, things like the Jacobian, and other kind of quantizations of change when several variables are allowed to move in this regard. Some of these have only application in 3 dimensions. Some of them only have applications when we're going to start to talk about vector fields. They all, curiously enough, use the same kind of symbol, a minor bit of abuse that will become clear later, except for this bad boy. The Jacobian we'll talk about more actually in the context of integrals. So in Calculus 1, we considered things that looked like this. Where our integrals are tiny sums, infinite sums of tiny steps in a certain direction along a certain length, weighted by the value of some function at that point. And we learned in Calculus 1 how this gives us the area between a and b of some function f. Right? That is the physical quantity that this is equal to here. On the other hand, there's going to be a proliferation of ideas about what the integral could be, in the same way that there is a proliferation of ideas about what the derivative could be, or what change could mean in the case of multiple variables. For example, just for a couple examples, right, we might consider instead multiple integrals over more complicated things, right? Maybe instead of over some line interval, maybe over an entire region. Instead of, well, I think we could call it a single area element, but maybe this is phrased in terms of multiple length elements over the same region R. And if there were some function that was doing the weighting here in the same way as before, maybe this would give us some higher dimensional analog of an area, right? Namely, we might be finding an entire volume underneath this area, or over this area. So instead, we might be switching from talking about lengths to areas, or even higher order notions of measure, volumes, etc., right? And then weighting them by some function and producing some quantity in that way. Another way that this might change is instead, we might be passing not over a one-dimensional space, but through some n-dimensional space along a curve, C. Or maybe now we're no longer talking about just 2 dimensions, we're talking about 3, or 1 dimension, we're talking about 3. And we want to know maybe something about, like, I don't know, how much energy this function is picking up as it moves through some field in this 3-dimensional space, right? We could even, calculate the length of this curve by integrating another kind of element. But this might be called a path integral. So we'll look at path integrals. We'll look at these, which I'll just call multiple integrals. And we'll look at polar coordinates and talk about changing area elements. That's where the Jacobian is going to come back into play. But that'll be, gone into much more detail later, I hope. And then finally, what we're going to want to look at is applications. Right? In Calc 1 and 2, we saw, how these might apply to physics. Specifically in Calc 3, we're going to want to talk about how these might lead to something called PDEs, or partial differential equations. But we also, in both cases, are going to have sort of fundamental theorems. So one of the ways you should think about a fundamental theorem is that it gives you some kind of backdoor to calculating some other quantity that you're interested in. Remember from Calc 1, we had this situation where if you knew some function, some antiderivative of f, then there was a sort of difference that we could take just plugging in those values, not having to do a Riemann sum, not having to do this, abstract or by the definition integration, but instead just finding this antiderivative and then evaluating it at the endpoints, evaluating it at the boundary of the line segment BA or AB. And what we're going to see is that this is actually a special case of a far more general theorem. And I don't know if I will get to express the theorem in its total generality. I hope that I'll find some way to work this in, because I think it's one of the most beautiful theorems in mathematics, period. But there is a sense in which information on the boundary of something is related to the derivative of that something integrated throughout a whole region. So this sort of tells you that there are two ways to calculate some quantity's integral that we might be interested in. Whether or not we're interested in the derivative of something, perhaps we can just look along the boundary. Now, this is not the true derivative. This is a differential operator. This takes a lot of background to build up, but many of the things that we look at are going to be special cases of this thing. This is one of them, right? Evaluating at a boundary gives me some information about a sum throughout a region. Provided I know that there's a relationship between this guy's derivative and the function that we're integrating. And in the same way, things like Green's theorem, Stokes' theorem, and this is a generalized version of Stokes' theorem. This is what it's usually called, generalized Stokes' theorem. The fundamental theorem of line integrals. All of these things are going to turn out to be special cases of this notion of generalized Stokes. So I hope to be able to cover that with you guys. But that probably is good for an introduction. We'll talk more about each one of those topics: vectors, functions of vectors, derivatives, and integrals. And then we'll get to applications in some sequence of videos from now. So thank you, and good luck with your studies.